Yeah, so first of all, I'd just like to thank everyone for all their brilliant and amazing talks. I've really enjoyed it, and I hope you will enjoy mine. So I'm going to present some results on vector field winding, as it says. This is sort of reasonably generic. I'm not talking about a particular physical system, although I will occasionally mention them. And it's in collaboration with Anthony Yates and David McTaggart. And I'm going to try and end with a question, which I'm hopefully going to convince you is worth your time helping me answer. Okay, so so this goes back to my thesis, and it's something we've seen a few times already over this this period. And we're talking about the winding of curves. So we've got this domain here, which is broken up into a slice of planes, like Mitch Berger was talking about in his talk. We've got this very familiar angle function now, this arctan function. And we're measuring the winding of a vector joining the two curves, this black curve, with respect to a fixed direction. And if you fix the end angles and allow these to deform by isotopy, it's invariant, okay? So in particular, I'm interested in vector field calculations, sorry. And in this case, I'm gonna focus briefly on fields where the integral curves of the vector field flow through the domain. Right, so they're all going from one cap to the other cap here. And it's a vector field, so we don't have isolated pairs of curves. But what we can do is we can isolate a curve, say this green curve here, and measure that winding, as described on the previous slide, with respect to all the other integral curves of the field, i.e. with respect to the rest of the vector field. And so we'll call, and one of the point here is, if all the field lines are flowing through the domain, every point on this disk D0 at the bottom, we'll call it D0, is associated with a particular curve. So this will actually define a density at each point on this lower disk D0, associated with the average winding of each curve with the vector field. Okay, so that's this integral here. Okay, it's integrated over the winding of one curve of the rest of the field. And I can define this for every curve of this integral field. So I make every curve a green curve. And I'm going to get a distribution like this of the winding. So this is blue if it's negative, red if it's positive. And what it shows here is actually this field is highly entangled. It may not have knots, but it's incredibly heavily braided. Okay. I think Gunnar might be talking about the relaxation of this tomorrow. So you'll see more of this field. Okay, so we've got this distribution. I'm going to talk about what this distribution can tell us about the evolution of this field. So an important point to make here, and this is going to be one of the crucial aspects of this talk, is that I'm not actually restricting to fields in a cylinder. So we're talking about domains which are homeomorphic to a cylinder. So they have a lower disk S0, an upper disk S1, and they have field lines which flow through the domain. So there's a tangent condition on the vector field and the side boundaries. And I've got some map F, which takes the cylinder to this heavily distorted domain. I'll be more precise about what I mean by this distorted domain shortly. But and under the pullback of this map F, I've got a vector field on here, whose winding I can measure as described in the previous slide, and in particular, whose winding distribution I can measure. All right. So the question is going to be, I've got this domain M. I've got two vector fields on this domain, okay? And I've got their distributions of their winding. And if their winding is the same, the theorem we proved, this is myself and Anthony Yates, shows that we can link these two fields by an isotopy which vanishes on the end boundaries if they have this same distribution of field line winding. Okay, so it categorizes the topology of the vector field. And in particular, it then says if I did a time evolution of this field and it changed, it implies there's been reconnection, there's been changing topology. So nice thing to point out actually from the conference in Venice that Renzo arranged quite a few years back, I had a conversation with Clayton Chunkwala over there, and he helped me understand by link to a paper that the constraints on this map F. So the domain just has to be a Lipschitz domain. So it can have like folds, quite sharp folds. It can be heavily entangled and knotted. It can have wildly varying cross-sectional area. So it can be a very arbitrary sort of deformation. The field is also Lipschitz. This means that we can, what this means crucially is that the mapping of the field lines from disk to disk is a diffeomorphism. And that's going to be crucial in the proof because it allows us to link the topology of this field to the group of diffeomorphisms of the disk. And we basically can't have knotted field lines in this domain. So apologies to all those who like knots, but that's the constraint. Yeah, so a crucial point to make is I use this a lot in MHD, so with divergence-free fields, but there's absolutely no requirement for that theorem that these fields are divergence-free. So very briefly with the proof, one way is very obvious. The other way, essentially, we show that if the field line mappings are the same, sorry, if the winding distributions that we can calculate are the same for the two fields, then the map of its field lines from the bottom to the top boundary, the map of its integral curves, must be the identity. And then we use some results from the groups of diffeomorphisms to show that that means there must be an actual isotopy between the two fields. Okay? And this builds on a lot of work we've both done previously with various other authors who are here. So how do we use this? So Anthony and I had a couple of papers out looking at vector field data or plasma data from a plasma experiment at UCLA. So this thing here in real life is a 30-meter tube filled with plasma, and they fire currents through it, which create magnetic flux ropes. And these flux ropes then reconnect and tear each other apart. And so they've got probes in there getting the magnetic field, and they're trying to sort of figure out what happens to the field. So they're trying to actually measure reconnection happening in practice. And what we found when we analyzed this data, this is a distribution of the winding. That's that quantity we're calculating, the total average winding. It basically goes through a cyclic reconnection cycle where it forms a single flux rope through reconnecting and then crashes and they separate apart. The reason it goes under this cycle actually is because it's constantly being subject to current. And then what happened is we use this result to actually measure the reconnection, which is the red curve here, and you'll show it peaks at troughs of the blue curve. So we can, and yeah, I think one of the important points was a quirk of the experimental data was the fact that the domain was a very funny shape. So we needed this sort of general domain. That's why we needed this map F in the theorem. So now one of the points I want to make about this is this is a sort of elemental quantity, I believe. So it's clear that if I've got this winding distribution for my field, the average winding of one of the curves with the rest of the field, I can multiply at each point on the lower domain, the disk, each field line with another quantity W. And if that quantity itself doesn't change in time, then this weighted winding distribution will also stay fixed. Okay? Now that might sound a bit arbitrary, but the point is, anyone who's ever worked with magnetic helicity or vorticity, you've basically been using this all along. So an example of that function is the Jacobian of the map F. So that's the map that takes this S0, this lower disk, which can have a very funny shape, to the disk where we actually measure the winding. So this has a Jacobian. So some information about the volume of your domain. And also, most magnetic fields have a strength or a flux associated with them. In this case, it's actually the normal component of the field strength. So I have this other function, Bz. And you can think of this as saying, well, I'm going to weight each field line with a field strength, right? But this is going to create a distribution, which we showed in the paper is formally equivalent to the field line helicity. And its average is actually formally equivalent to the actual helicity. So the point to make is that the helicity, this quantity a lot of us are used to using has this extra information tagged on. And for example, the Jacobian encodes the information saying that I can distort and deform this domain. I can change its volume, because remember, helicity, vorticity, these are volume quantities, right? These are volume integrals. So the Jacobian knows something about this deformation. And the point being here is, if I take this highly distorted field and I map it to a sort of deformed domain, I'm not actually undoing the entanglement of the field lines, because this map F has to be a nice map, right? So I can't undo the entanglement. I'm just changing sort of the volume and the shape of the domain. So that there is something under this map that's not changing this entanglement. The second thing is the field strength. I might input it at one end, but because when I'm looking at divergence-free fields, that flux quantity is conserved along field lines. This is just from the divergence theorem, right? So essentially, I'm pumping, if you like, I'm pumping the field lines with strength, but that's actually going to change the shape of this distribution. And if I was being really finicky, I could multiply every point in this domain, every field line, by a sort of the opposite of its strength, and make this distribution uniform. But it would still have this heavily entangled field line, because the strength has nothing to do with the field topology. All right? Be a bit of a weird thing to do, but I could. Right. So I'm now going to try and convince you that this is a physically meaningful distinction. So we're now going to jump to some work I did with David McTaggart. The paper was primarily aimed at sort of MHD type folk, but I think the conclusions are quite general, actually. And from hereafter, I'm still talking about this vector field winding, but I'm not so worried about my domains being these tubular type domains. I can have knotted field lines here now, right? This doesn't require that. That's only for the uniqueness theorem. So if I want to split the field into its strength and its topology, I just say, okay, well, my vector field, whatever it is a field strength times by a unit vector field, okay? And the unit vector field obviously is the thing that determines the curves, the integral curves of the field. So it's the thing that contains the topology. Then there's just the strength. I'm then going to assume just an arbitrary evolution of this field. This is not specific to any particular physical model. I'm just saying the field will change. Part of its change will be directed along the field direction itself. And the rest of its field length, the rest of its change, sorry, will be perpendicular to that. Just simple saying we've got to break this thing into two parts. If I then look at the evolution of the unit vector field, it's only affected by the sort of out of field line direction. And if I look at the evolution of the strength, it's changed by the parallel component. So the strength and the topology, their evolutions are affected by the two different components. They have different physical evolutions. And again, this is not specific to a particular model. And in actual fact, if we do have a field which has a sort of Dirichlet type energy, so the dot product of the field, this actually tells you that it's only the component along the field line which changes the energy. And this kind of goes back to the comment Gunnar made yesterday that the reconnection, the changing topology, is not directly, immediately changing the energy of the field. In a nonlinear evolution, of course, changing the topology will eventually change the energy because it has a direct effect on this term in the later evolution. But this is sort of showing what Gunnar was talking about yesterday. Reconnection, at least in that kind of model, is not changing the energy of the field directly, immediately. It only does so through relaxation. And I'll give you an extreme example to try and convince you. So David found this example, and I think it's just fantastic. So we're now going to look at quite a specific field, which is very common to fluid dynamics and magnetic field theory, which is this linear force-free field, or this is a non-integrable field. We saw a very nice talk about that earlier, where we've got the curl of the field is equals to is directed along the field times by a constant alpha. And this, as David was talking about, is a minimum energy of the field subject to a fixed helicity. And I believe it's very important in vorticity models as well. That's not quite my field, but pretty common field to see. And I'm now going to make it quite specific, a purely resistive evolution. So you could either think this B is a vorticity field or a magnetic field, and it's relaxing under a resistive or a viscous evolution. So it should be changing its helicity. And in theory, it should be changing its topology, right? Now, David found this lovely result by this guy called Jetta, I'm not quite sure. It's from back in the 60s, I think, or the 70s. And it basically says, under this evolution, this field will stay in that form for all time. Doesn't mean the field stays exactly the same, but it means it stays satisfying this linear force-free equation. So I can put this in the evolution equation, and I can actually consider it's keeping this form for all time. And when you substitute that in here twice, you end up saying that dB dt is equals to alpha squared resistivity eta or viscosity times B. So it decays as a Gaussian, where B at naught is its initial field shape topology. The field topology is not changing here at all because it's purely relaxing in a scalar manner. That means the unit tangent field is not changing whatsoever. Its field line topology is exactly fixed. All that's happening is the lights are going out in this field. Its strength is going down. And of course, that means that the helicity decays directly to zero, whilst the field line topology stays fixed for all time. So we're kind of used to thinking of the helicity. Sorry, I misspelled it. We're used to thinking of the helicity as a topological quantity, and it very much is in a sense. But there are cases where it very much does not behave like a topological quantity. And this distinction between field line winding and helicity, strength-weighted topology, is very meaningful. Now, when I was talking about deformations of my domain earlier, like expanding my tube or whatever, one can think of this relaxation as being a bit like crushing the volume of my domain. I'm not actually changing its shape. The volume here, so to speak, is the strength, if you like. But it'd be equivalent to doing the helicity integral in an ever-shrinking domain, but with the same curve topology. So it's a bit like saying this is a diffeomorphism of my domain where I shrink the domain down, but I don't change the shape of the curves at all, right? So I'm going to come back to that idea in a bit. And in fact, in the paper, I went into quite a bit of detail about the general form of these two functions under this resistive evolution, but it's way too complicated for me to introduce quickly here. But there are lots of components changing the topology and lots of components that change the energy or the field strength. And non-linearly, they have a very complicated interaction. But so David and I have been using this quite a lot over the past few years in trying to measure the inputted topology of magnetic fields in the solar corona. So solar corona is sort of like the lower surface, it's the lower atmosphere, sorry, of the sun. And we can't see the magnetic field, so to speak, in the sun, except at the photosphere, except basically at the point where we pass from the interior to the exterior of the sun. So imagine this plane is a slice of the photosphere of the sun's surface. We have magnetic field data on this plane and nothing else. And so the aim of the game we play is to figure out what kind of topology is being shoved into the sun's atmosphere, because that has huge effects on solar weather. And imagine a scenario where we have this twisted flux rope. It's a right-hand twisted flux rope, magnetic field. It starts underneath the surface and then it just rises up steadily and moves through the surface. I'm going to let it rise up like this, and then I'm just going to pull it back down a little bit so that the core stays well above the surface. And if you calculate the helicity and winding inputs in this case, the winding input is this dashed line. So that's just the helicity without its field strength weighting. It shoots up as the core passes through the surface and then plateaus out. Whereas the helicity kind of goes up. And then when we reach this point where I start to pull it back down a little bit, remember I'm pulling it back down so that its core stays up, the helicity starts to drop quite dramatically. Now, the reason for that is if we go back, we know the helicity is the vertical component of the magnetic field multiplied by the topology, right? And the vertical component is quite strong when this field is quite vertical. So here, where the foot points are, where it's coming in vertically, the helicity is very obsessed with that bit. So when I pull this back down, its foot points kind of have a big effect. Whereas the winding is much more concerned by this bit, which it sees the topology, the twist of the field flying through. So when we do proper MHD simulations of flux emergence with convection going on, the convective flows beneath the surface pull lots of bits of the field back down. That's these blue lines. It's a complete mess. It's nothing like that lovely flux rope picture. The helicity, by the way, this is a negative flux rope, changes sign, whereas the winding has this nice plateau. And we did loads of experiments of vector fields emerging with varieties of topology, but with some net entanglement, sorry. And the winding is really consistent. It always has this sort of plateau-like signature, whereas the helicity gets all sorts of confused by this measure. So it behaves very inconsistently, whereas the winding is very consistent. It says you've shoved a load of topology into the atmosphere. And so we've used this basically to, first of all, demonstrate the first sort of observational evidence that flux rope topology, magnetic field topology of so-called solar active regions is largely created beneath the surface of the sun. There were competing hypotheses sort of before this. And second, we've managed to use this winding input data to predict when certain activities called solar flares happen. And these are basically when this complex magnetic field undergoes a rapid reconnection and sort of fires bits of itself off into space. And the field line winding, so when I remove the strength of the field, this more elemental quantity is seems to be much more consistent in making these predictions. So hopefully I've given you some argument that this distinction of this field line winding underlying these sort of topological quantities is a very important distinction. So now the question. So this is sort of very well-known result in our field, right? That a few of the people here have been involved in, which sort of says that any regular invariant of a volume-preserving transformation is equivalent to the helicity, or it's a function of the helicity, right? Now, I'd like to propose or challenge you to say, I think any regular invariant of a diffeomorphism, homeomorphism, that includes compressive transformations where you're crushing the shape of the domain, you're twisting it, you're distorting it, whatever, is equivalent to the winding. So there's this more fundamental quantity underlying a lot of these topological quantities that we're seeing in sort of volume preserving evolutions. Now, the point is, it's not to say that the volume preserving part isn't hugely important, the helicity isn't hugely important, the strength is very important, but that a lot of that extra information comes from the physics you're using. So if you have a compressible system, you don't want to use the helicity, right? There's a few people going to be speaking about this, but I think there's something underlying it, and it's quite a tough task to prove this, and I think there are people who are better qualified to help me. So any advice would be very much appreciated, and thank you for your time.